All right. So next up, we have Fernando.
Yeah.
Okay, so you're up on the screen. So Fernando's going to talk about liquefaction and where his technology and his solution applies to. So you're looking at both metals and separating out uranium. Fernando?
Right. Yeah.
Okay.
I'm ready to go.
Okay. I'll turn it over to you.
Thanks. Well, good afternoon, good morning, wherever you are. My name is Fernando Vaz. I'm a founder of SmartDry. I'm a biologist with a PhD in England in biotechnology, and my interest in mining is due to the environmental impacts of the mining sector. About 2.5 years ago, Vale, the iron ore giant from Brazil, launched a challenge to dewater iron ore on pre-embarkation of ships. And I submitted a proposal. I got some money from them to develop the technology, and this led to the development of a new dewatering solution. And during the dewatering solution experiments, I noticed that ultrafine black grains accumulated at the bottom of the dewatering equipment. And that puzzled me. I went after an explanation, and the explanation came from a Japanese researcher that published a paper on how the grains move in saturated soil during the cold earthquake. So for my amusement and completely unbelievable, grains do move during liquefaction effects. And if they do move, you can do mineral separation. And with that, a series of applicability opens up in terms of opportunities. So we are hard tech in Brazil, which is extremely challenging because investors in Brazil don't see hard techs, don't understand it. They only see digital and things like that. The leachable market is immense, right? All these metals are leachable, and iron is also bioleachable if you want to extract from tailings and things like that. So in terms of value, we only lose to crude oil, right? The sum of the leachable metals are over $1 trillion per year in value, right? So what is leaching? Well, leaching has two main areas, okay? One is the chemical, which is for each metal or has a kind of process, a recipe, if you like, of chemical solutions, process and things that will leach or extract the metal from the source. And then there is the mechanical side of the process, which basically you see three kinds of different solutions: tank, heap, and in situ. Heap and in situ are what I call mechanical, almost non-existent. It's very passive process. In heap, you simply drop the lixiviant on top of the pile and it percolates down. In situ, you have one tube that injects the solution, then migrates, and then the other tube takes it out. So these two are very passive systems. The tank is a place where you put the material with the lixiviant, and under agitation, you make the lixiviant dissolve the metal. The problem with this is it's very high capex and opex and can be applied only to very high quality grade material. So this is the classical heap leaching, and in terms of uranium, in the United States, it's not much use because the United States produces uranium. 50% of its production comes from in situ leaching. But globally, in terms of uranium, this represents about 47% of the total extraction of uranium. And of course, uranium is a strategic and an energy metal, so very important. The problem with heap leaching are several. It creates puddles on top of the pile. It creates preferential drainage channels and all these kind of things. The net result is that a very low efficient process, between 50 and 80%, depending on several factors, that you can actually remove the metal. In terms of tank leaching, the percentage rises quite a bit. It can get to 95, 96% efficiency, but it's still very costly process to be done and restricted to very high grade ores, which are becoming more and more difficult to find. If we compare inverted leaching, pile, and tank leaching, you can clearly see the advantages of inverted leaching over these two present technologies. But you might be asking, okay, Fernando, so what is this inverted leaching of yours? Okay, this is manganese waste or tailing, right? And in these tubes here is being injected water. It's just to exemplify what happens during inverted leaching. Here is not actually happening inverted leaching. It's just recovery of metal. But as you can see, you inject the lixiviant and apply vibrations. What happens is the lixiviant rises through the material that it's under vibration. So the grains are rubbing against one another with high energy impacts. This should increase efficiency in extraction. When you get to the point that a liquid layer is formed on the top of the material, you can take the lixiviant from here and recirculate it down and as many times as you need it to get it fully saturated or complete extraction of the metal. So this is it. This is what this new mechanical process of leaching is all about. It's a contraflow mechanical process that has not been seen in the mining or in leaching markets, and it brings quite a lot bunch of innovation. Okay, and it can be done in one step or in two steps. One step, you take the material, mill it, put inside the equipment, and inject the lixiviant and keep recycling. Once you get it saturated, you take it out. The two steps is where you can first, using liquefaction, create a concentrated metal. You inject water first, do liquefaction, separate dirt and metal layers, and then you take only the metal layers and put in here. The importance of this is that in both one step and two steps, you get the leachable metals out in the lixiviant, and at the same time, simultaneously, all the insoluble metals are recovered because they form a layer at the bottom of the equipment. This means less acid mine drainage, less ESG impacts, environmental, social, and governance impacts. More profitable because you're not leaching, you're not getting only the leaching material, but also the insoluble metals, which is our view of the modern new mining sector. You're going to mine all that is present in your ore, not just one or two or three target metals. You're going to mine all, right? Because there are people that are willing to buy anything that you can think of. In terms of dewatering, this is the volume of all the metals we mine. It's huge, right? Of course, iron, it's by a long way the most important in terms of volume, but copper, which is only 22 million tons per year, is the metal that produces the most quantity of tailings in the world. 40% of 282 billion tons of tailings deposit around the world come from copper, right? And then after copper, iron, because of the volume you mine every year, and then in third position, gold, right? But there are 282 billion tons of tailings, and these tailings have metals in it that liquefaction can recover and can dewater. But you're going to say, Fernando, why dewater tailings that are deposited in tailing dams? Well, I can tell you that BHP and Rio Tinto in Atacama Desert are struggling with water. 75% of the mining in the world are done in areas that water stress is a problem. BHP and Rio Tinto in Chile need to get the water from the tailing dams because the world changed. Local communities are putting pressure, everybody's putting pressure, saying you have to be more efficient with your water, right? Water is first for people, and this, they are really looking for a solution there. The problem is volumes, right? they produce 30,000 tons of tailings on every single day. So they are looking for a dewatering solution. In terms of dewatering, our technology outperforms all the other mechanical solutions. In terms of the cycle, it's very fast. We can dewater a huge amount of material when compared to the other technologies. Our equipment costs much less and consumes less energy, right? Which brings all together to a more efficient process for dewatering. And this is, dewatering in zinc tailing, right? 50% water, 50% solids. What you do is you apply vibrations. You apply vibrations for 1 minute, right? It's not being injected water. It's just that my equipment can do both things, but this is just the water that was present in the tailings, 50%. You apply vibrations for a minute, and in the end, you remove the water using a suction device or siphoning. You have this material that is dry stackable. And here you can see showing dry stackability. What this means is that there is no more free water in the intergrain spaces. This material you can put on the ground and compact it. This is what the mining industry is looking for. They are not looking for to dry tailings, because the actual drying means using thermodynamic solutions with a very high cost. No, they want to be able to put the material on the ground and compact it and make it safe. And liquefaction does it in a much better and more efficient way than the other mechanical available solutions in the market. So this is us. Our technology has a broad application. We can recover grains, metal grains from tailings that are ultra fine. We are talking to oil companies to use liquefaction to convert oil sludge into circular economy products using liquefaction effect, again, with advantage. And we can even apply this to recycling products, mining, landfills. There is a big broad of applications. Sea mining, it needs desperately, in my opinion, a dewatering solution to make it viable, the logistics of bringing the solids from the sea or offshore to land onshore to be processed. Of course, you can process offshore, but the cost of it's quite prohibitive. It's much cheaper to bring the solids and process everything on land. So this is our technology. Our business model is based on manufacturing the equipment and selling, or hardware as a service, but our exponential growth will come from the technological fee that we're going to charge, because our equipment costs much less, produce much more, so we can charge a tech fee that will increase the amount of revenue every time we install a new equipment, without increasing the costs for running it. 3 people will run the financial market, the financial sector, charging, insuring, charging lips. So this is us. In terms of team, it's myself, and I have 2 potential co-founders in the United States, and I have a vesting contract with them. But we are looking for investors and grants, right? Here in Brazil, I also looking for grants to develop pilot plants. And yesterday I got a great news that I'm going to do a POC project in Peru with a mining company that mines zinc in Peru. Right? So this is us. This is our technology, and I can answer any questions that you may have.
All right, so Fernando, is it scalable, and to what size? I mean, can you go down in scale, up in scale?
Yes. This Peruvian process, for you to have an idea, they have a waste that is almost pure copper. It's 60% copper. It comes from the metallurgy process of the zinc mining. And they have only 40 tons per day. The problem is this material has a density of 6.3 grams per cubic centimeter. So the thing is so dense that if you try to use present mechanical dewatering solution, it doesn't work because it settles even before a press filter or disc filter can act, or centrifuge for that matter, in the water. So the equipment can go from, let's say, 2 tons per batch up to 100 tons per batch, right? It's fully desirable, and you can have any kind of size in the equipment. For both inverted leaching, recovery, and the water, it's fully customizable to the client operation side.
Okay, the water. So once you go through the liquefaction process and you've added the chemicals, I guess there are chemicals that go into this to help to condense the material. Is that correct?
Not
Or is it
really.
just water? Okay.
If you're talking about dewatering, I take the material as it comes out of your process and put inside my equipment, and I separate the liquid from the solids via liquefaction. The water will come out with some solids in it, okay, very small amount. It depends on the characteristics of material we are dewatering, but normally very small amount, because there is no filtering device involved, right? Just vibrations and liquefaction affecting. So the water can be either passed to a sedimentation pond and then a filtration system to be reused in the process, or even treated to return to nature. Depending on treatment, the use of it is somebody else's solution. We at the present we are not entering this water treatment phase.
All right, so it's not like trying to pull gold off of metals or anything like that, where you need a chemical to actually separate that bond.
No.
You're just using water.
No. In liquefaction, what makes the separation is the difference in density and the tendency of the grain to stay inertia, right? To stay to stay stopped during vibration. That is, the heavier, the denser the grain has more inertia to stay put, stay stopped. And the lighter, it has less. So that's what causes the actual mineral separation of the process. In the inverted leaching, then you're going to use a lixiviant, right? That it's normally either a strong acid or a strong alkaline. And this is a chemical process that we need experts from to do it. That's one thing that I'm doing here right in Brazil, is applying for grant to be able to hire a chemical engineer expert in leaching, join the team and develop this for a very particular opportunity here in Brazil with a kaolin tailing that has a higher concentration of niobium, tantalum, and 2 other metals. The people been mining kaolin in Brazil for over 60 years and throwing away the metal, which is much more valuable than the kaolin itself, simply because they don't have the technology and they don't have the knowledge to extract the metal. And with the inverted leaching, we really think we can do it in a more profitable way, because the amount of lixiviant that is needed, it's much less. In tank leaching, for instance, or pile leach, you're talking about 2, 3, maybe 4 times in terms of volume per mass. In inverted leaching, we are talking about 25% of the mass in volume. So it's a quarter of the mass in terms of volume of lixiviant. And this drastic reduction in the volume of the lixiviant impacts costs upstream when it comes to the actual precipitation of metals from the lixiviant solution.
So is that solution, is that hazardous, or can that be neutralized?
Yes, it can be neutralized. Yes, it can be neutralized. In our technology, we intend to do is this. We will inject the lixiviant to extract the metal. Then we're going to do a washing step that we're going to inject water to remove the last lixiviant that is still there. And after that, we're going to do what we call a neutralization step. So for instance, if the lixiviant is a strong acid like sulfuric acid, we're going to inject alkaline product like lime or something like that, that will neutralize the pH and bring the pH around to 7. So whatever tailings are left will be pH neutral or close to neutral. And this will allow us to use this material in mine closure, recovery area, this kind of thing. And remember, we are also extracting the insoluble metals in the same process, meaning that we are reducing drastically the occurrence of acid mine drainage from this material. It's a very interesting new technology.
And so now what about
Sorry, Kurt. What about what?
issues and
I didn't
could you
get.
clean up an area? Environmental application, you hear me?
Yes, we can.
So,
We are.
yeah, 'cause I was thinking if you had like a diesel spill on land or something like that, would you be able to
Yes.
recover diesel from it and do a dirt or a fill that was non-hazardous?
Diesel free. Yeah, we can, because all we need to do is, let's take this example, the diesel, right? Diesel doesn't mix with the water. So what we have to do is put the material, the contaminated material inside the equipment, inject water at the bottom, vibrates, the water will rise, passing through the material and forcing the diesel up, right? Removing it from the grains. And then you're going to have a diesel layer on the very top, a water layer, and solid, and we can recirculate the water as many times as needed until we get total removal of the diesel from the soil. The other thing that can be done also in the US, there are a Manhattan Project legacy with uranium and other radioactive waste in several areas in the United States. This can be used for it also to recover and eliminate the radioactive material from either soil or tailings, waste, anything.
All right. So when you're talking about doing it on a large scale, where you're talking about several hundred tons, does it matter that there are rock, stones, boulders, other things, tree branches, whatever?
It doesn't matter if you're trying to decontaminate it like the diesel, right? Then it doesn't matter. But in my opinion, if you're gonna have to do this, you want to be sure that there is no other metals there also, because it's very common to have, right?
Right. Yeah, rusty barrel.
Yeah, since we're gonna do the thing that we will also separate the metal, right? We pay attention to. But in terms of metal separation, yes, grain size distribution is a critical factor. Then if you have rock boulders and this kind of things, it doesn't work. But if you're trying to remove contaminant only, then it doesn't matter. Grain size is just a mechanical process that will force contaminant upward. Of course, depending on the characteristics, the diesel, it's quite easy. But my knowledge of chemical spills are quite limited. But imagine that you have a material that it's not water soluble or will not, for some reason, it's not lighter than water. Then we're gonna be in trouble trying to remove it. If it is like diesel, that it has a lower density than water itself, no problem. If not, I'm gonna have to ask for a chemical engineer saying, okay, if not water, what is the solution that I can inject here to remove this contaminant by either dissolving it or forcing it to rise as whatever liquid I'm injecting at the base. And liquefaction will force it go up, passing through the material. It's how can I say? It's a mechanical solution for a very broad application. That's the beauty of it.
Okay, so now on the metal separation, do
Yeah.
you take it beyond the conglomeration of metals? So maybe what you end up with is like 80% iron, 20% copper, 2% gold, whatever. You then separate those, or is that left to someone else?
Well, if I have the capital, I'll do the separation myself. Simple as that, right? But hydrometallurgical or pyrometallurgical process are capital intensive. Of course, depending, I can give you a classical example. There are about 20,000 sites in the United States from the gold rush era. These sites are contaminated heavily with mercury, but they also have very good levels of gold. The problem is, the gold companies want to mine it. Local communities say, hey, you're not going to mine the gold and leave behind the mercury. You're going to have to remove the mercury to mine the gold. And that's where the problem starts, because there was no technology that could do both. Either you recover the gold with carbon in leaching or any kind of process, but the mercury was left behind. With this technology, you can recover gold and mercury and iron and aluminum. It is present in the material and clean in the process, clean. So the actual dirt that we're going to return is going to be clean mercury, gold, metals, and things like that.
All right.
And there are 20,000 of those sites in the United States.
Yeah,
It's amazing.
I can imagine, and I can see.
Yeah, in California, for instance, the water, the mercury in the water level 3 times higher than any other place in the United States, because if you put the EPA level in California, you cannot drink water in California. You cannot use water in California. Such is the level of mercury contamination in the Sierra Nevada and all those areas that were heavily gold mined in the 19th century, the gold rush, and left behind tons and tons and tons of mercury. Quite shocking, but it's
So then you can actually track these from water, what you're saying?
from the material, from the tailings that are left behind. Because in the 19th century, what you did was you take the material hydraulic. Most of the mines were hydraulic mine, right? So then you took the material that it comes out like paste, passed through vibration screens and things like that. So you get the nuggets and small grain, but the ultra fine grains of gold escape, right? And then you get a concentrated, and then you add mercury to it to do amalgamation, and then you take the amalgam, burn it, and then you recover the gold. But during this process, also mercury escape and end up in the tailings. So there are some places in the United States where you find between 0.6 to 1.5 grams of gold per ton, but the problem is you also find 0.6, 0.3 grams of mercury, horrendous amount of mercury, and of course there are iron and aluminum also in this. But when people mine gold, say to them, "Oh, there is iron," and the guy say, "Yeah, iron is $100 per ton. Gold is $60,000 per kilo, $60 million per ton." They don't look at. The problem is my technology. You get it both at the same time without having to do anything more. So I am
reap
the one that's
all the benefits.
Exactly. Why not?
Yeah, no, that makes sense to me.
Yeah, there are some surprises. Okay, like I just in December I did a test with manganese. The first test I did with manganese was last December, and manganese has a very high density, much higher than iron. So I was expecting a quite straightforward mineral separation. With this high density, it's going to be beautiful. The moment I start the first step, I looked at the equipment. I said, there is something strange going on here, because the water was black. I could see that there was a lot of manganese in the water. And I say, what's going on here? Anyway, the tests showed that about between 22 and 25% of the water has manganese. 25 and 22% was manganese. And this puzzled me. I said, what on earth is happening here? And the answer is manganese oxide is a dipole molecule. And because it's a dipole molecule, it forms a link with the water, which is also a dipole molecule. So this very weak link for ultra fine grain is enough for the water to drag this grain. And you say, oh, Fernando, you're going to lose 25% of the manganese. No, you're going to have a new product, because manganese ultra fine spheres is what the EV battery needs. You need the manganese in battery. You want the smallest spherical manganese possible. And this material coming with the water is perfect for it. I'm about to do a calcination test on it and see if we can recover like 1 micron, 2 micron spherical manganese material. If we get that, we're going to send samples to the EV battery manufacturers and say, look, we have a new method of producing this. Would this be interested to you? Of course, there is a cleaning process involved, but we figured this out already, how to do it. We're going to use a high density grade column to do that, because the dirt is basic silica and clay, very light, and the manganese is very dense. So you put in a high density column and it's going to separate quite easy. But my technology allows us to recover this ultra fine grain, 1, 2, 3 micron in diameter. And in case, for instance, of iron, I recover grains that are all smaller than 150 micron down to 20 micron. In case of iron, they don't grind it as much. But the great opportunity there is decarbonization of steel. The industry is looking for a way to decarbonize, and the solution is hydrogen. The problem is if you use pellet and hydrogen, you are burning a lot of hydrogen to do that. I have an idea that take the dust, the ultra fine grains dust, inject in a new furnaces model with hydrogen plus microwave. The microwave is going to be the thermal energy. The hydrogen will be just the reduction agent, and the chemical reaction will happen and you end up with metal, iron, metal, water, vapor, and that's it. Full total decarbonization of steel. And a steel that has a microstructure based entirely in micrograins from tailings, smaller than 150. This is important because this increases steel resistance, right? The smallest the grain is, the more mechanical resistance and quality the steel has. So, but you see, when I talk to the people in the steel industry, they say, yeah, but we're gonna have to throw away all our furnace, build new one. And I say, yeah, you're gonna have to. But capital is available, quite cheap capital, because the governments finally understood that if we don't decarbonize, we're gonna go extinct. There is capital to do it, right? And the projections of savings of hydrogen alone pays the interest rate you're gonna pay in the loan to build a new furnace. So the numbers I crunch with public information available shows it's very doable, very realistic, doable. At present level of hydrogen costs around $4 per kilogram. If it drops to, well, then it's because presently using pellet or synthesized grain, you burn 54 kilograms of hydrogen per ton of steel produced, pig iron. Our production says that we're going to reduce this between 20 to 30%. So quite a reduction in the amount of hydrogen you're going to use.
Yeah, no, I definitely see applications with Department of Energy. Understand why you need a chemical engineer as well.
Yeah,
National Science Foundation, those kind of places.
Yeah, that's it. But you see, for instance, like I'm Brazilian, so I cannot apply for some kinds of grants because I'm not a US citizen or I don't hold a green card, right? I'm in the middle of a grant submission with the DOE for nuclear fuel chain. We're gonna apply our technology to uranium extract from ores, tailings, and even contaminated soil with radioactive material. But we had to do kind of a business engineering first. My two founders in the United States have working permits. They are not American, have working permits. So the DOE say, okay, if they hold 51% of the company, yes, you can apply. Yep. And then we did this. We said, okay, no problem. We have an understanding with us. And let's see if DOE likes our idea for nuclear, but it has to go to others. It's section 58, subtopic other, because it's so off the curve, something so new that they didn't think of. The person in charge of the program said, use the other subtopic, but she actually said, please. It's very good for phase one. $300,000, $200,000. We can do a lab equipment and run the tests with uranium ore, tailings, and contaminated soil, and prove the technology work. And if we do that, then phase two is $1.1 million. Then we are cooking.
Yeah, we'll have to talk more after this.
My pleasure.
Definitely know people that are going to be interested. I got a project idea that I want to talk to you about. So definitely, I'll be following up anyway. So we'll follow up on those.
Great.
All right. Well, thank you for being here.
Thanks.
Do you have anything else closing that you wanted to?
No, not really. If anyone doesn't have any questions, I'm okay. I have Eugene has my contacts and everything. He knows he can share with everyone that it's interested in talking to. And we are developing opportunities in Brazil, in Latin America, but we also states because we see huge tailing mining. There are a lot of tailings in the United States with cobalt, nickel, zinc, you name it, iron and aluminum everywhere. But here in Brazil also, and the beauty of mining tailings is that the cost, very expensive cost, already done. You already blasted, crushed, mill it, transported. The thing is stored either in a tailing dam or in a tailing deposit facility. All we have to do is dig it out, put inside my equipment or our equipment, liquefaction equipment, and do whatever we want. If it's leachable metals, we're going to do inverted leaching. If it is insoluble metals, we're going to do mineral separation or recovery of the fine grain and so forth. And there are thousands of tailing deposits that are left. Company went bust. EPA has a problem with it. DOE has a problem with it. DOD has a problem with it.
Yeah, no, definitely.
So imagine we can go to EPA and say, we're going to clean we're gonna mine, and it's gonna solve your environmental problem in one operation. So
Right.
it pays us to clean, we get the metals, and everybody's happy.
There you go.
It's
That
huge
works.
potential in the United States. Huge.
Yeah, no, I can understand.
And
So
the environmental authorizations are either in place or once were issued. So if you get to EPA and say, look, we're going to clean it, are you going to make fuss towards issuing us the permission? I don't think they will. They will love it.
so have you developed any white papers? Post?
Yes, I do.
Okay.
I have
If
some.
you can,
It's in the cloud. I
yeah, if you
I
can,
can send it over.
yeah, if you can share those with me, and I'll make sure that they get posted.
Sure, no problem. We'll do.
All right.
I just need an
Thank you
email.
much.
Okay, pleasure.
All right. Take care.
Same.
All right. There's a lot of great ideas and a lot of great technologies out there, a lot of great applications for what we presented today. Please, share your thoughts if you view this post today or post live, and put your comments in the comments. We're looking for ideas and applications that you see. And Fernando is also looking for a chemical engineer. If there's a university out there that has interest in working, I'm sure that Fernando would have interest in talking with you. And that wraps it up for the second session of the Innovation Ecosystem Collaboration Forum.